Hi everyone, welcome to another episode of Physics Recap from JEE Mantra Series. In this module, we will be discussing 4 chapters: Magnetism and Matter, Electromagnetic Induction, Alternating Current and EM Waves. Alright, ready? So here comes the very first chapter, that is Magnetism and Matter. It's a very small chapter. Okay, so the very first thing that we are going to discuss from here, it is all about magnetic field lines. Point number 1, it forms a closed and continuous loop. All right, now next one, the tangent drawn at any point gives the direction of magnetic field. It's exactly the same way that we did calculated, or exactly in the same way we find out the direction of electric field using electric field lines. Exactly the same thing. Okay, and here also they are not going to intersect each other. They're not going to intersect each other, and the direction of field lines, regarding the direction of field lines. Okay, please note this. Outside the magnet, that is from north to south, and inside the magnet, that is from south to north. That is very important. Outside the magnet, it's from north to south, and inside the magnet, that is from south to north. You need to be very careful on that part. All right, next is magnetic dipole. What was electric dipole? There we were having one positive charge and negative charges separated by a finite distance. In this case, this time it's going to be a north pole and south pole separated by a finite distance. There we were having electric charge. Okay, we measured the magnitude of the charge over there. So here, instead of that, we will be measuring what? The pole strength. All right, so exactly what was the role of electric charge over there? Here the pole strength will be playing the same role. Now magnetic dipole moment. One more thing, the pole strength, the unit of that is what? Ampere meter. The unit of that is going to be ampere meter. You need to be very careful with that. Now what about the magnetic dipole moment? What was electric dipole moment? That was Q, that is charge multiplied by distance of separation. So here it is going to be pole strength is marked as small letter m here. Pole strength multiplied by 2L is the distance of separation. So magnetic dipole moment, capital M, is going to be pole strength multiplied by the distance of separation. All right, coming to the unit, it is joule per Tesla or ampere meter squared. Joule per Tesla or ampere meter squared. Now comes some special cases. How to calculate the magnetic dipole moment for a given magnet under certain conditions. So initially we are having a bar magnet whose pole strength is smaller prime and distance of separation is 2L. Now in this case number 1, in this case what I am going to do is that you can see this is made into two halves like this. One part is there and another part is there. All right, so what happens here is the pole strength that remains the same. That means if the bar magnet is cut in this way, the pole strength remains the same. And in case number 2, you can see that it's cut along the length and here it is perpendicular to the length. So in this case, M remains the same and L become distance of separation with the poles become what? The half of that. So just because of that, you can see that the new magnetic moment M dash is going to be M into, initially the distance of separation was 2L, and now it is divided by 2. All right, so what happens here? This is going to be M by 2. All right, here, because you can see this particular part was what? This was M, so it's going to be M by 2. That means it becomes the half. All right, now in this case what happens is, here in this way we are dividing. Okay, so what happened to the pole strength? That will become half. So M will become half and length remains the same. M become half and length remains the same. So M become half means going to be smaller m by 2. This is the magnetic pole strength that reduced to half of its initial value, and the distance of separation is going to be the same thing only. So there also what happens is this one and this one will cancel each other. All right, so you may see the same thing, isn't it? The distance of M by, one second, yeah, M got M by 2, distance of separation is the same. All right, so in this case what happened is, it is this one and this one is getting cancel each other. Earlier it was M into 2 times L, isn't it, divided by 2. So what happened is it reduced by half. So here also it becomes the half. So the section of the bar magnet, whether it is perpendicular to the length or whether it is along the length, what happens to the magnetic dipole moment is that will be reduced to half of its initial value. Now comes the next. Here you are having the bar magnet and that is best into a semicircular shape. So what happens is basically the pole strength remains the same, but the distance of separation is now changed to 2 times r. Earlier it was 2 times L, now it is 2 times r, where r is the radius of curvature. So in this case what happens is m dash is going to be 2m divided by pi. M dash is going to be 2m by pi. Now you can see I'm having 2 bar magnets. All right, it's kept perpendicularly like this. That means the length is kept perpendicular to each other. So if capital M1 as well as capital M2 are the magnetic dipole moment of these 2 bar magnets separately, then the resultant magnetic moment is going to be under root of M1 square plus M2 square. It's the same concept that we used to do in case of vector addition. We are just considering the vector sum only, because you know that magnetic moment is a vector quantity, and what is going to be the direction? That has to be from south pole towards north pole. Their electric dipole moment, it was from negative charge to the positive charge. Here it is magnetic dipole moment, that is from south to north. Moving to the next, we are having 2 bar magnets again, but this time it is not kept perpendicular to each other. They are having, so here this is M1 and here this is M2, and the angle of separation is theta. All right, so the resultant of this is marked as capital M, and that is making an angle phi with respect to M2. Let me sync this with the figure. So let me take this as M1, let me take this as M1, and let me take this as M2. Okay, so I repeat once again, we are having 2 bar magnets of magnetic moment M1 and M2. They are kept at an angle of separation of theta. The resultant magnetic moment is M, and the resultant magnetic moment is aligned in a direction, so aligned at an angle of separation of phi with respect to M1. Under that case, M dash, that means the resultant magnetic moment, here it is marked as M dash, I marked it as M here. So again, giving the same notation. So M dash is going to be under root of vector formula we need to apply. Here this is going to be M1 square plus M2 square plus 2 times M1 M2 into cos of theta. All right, and what about this angle? This angle tan of phi. Okay, tan of phi, that is going to be, here it is M2, so this time it's going to be M2 sine of theta. All right, all divided by M1 plus M2 cos of theta. All right, was that okay? Moving to the next, that is magnetic field due to a magnetic dipole, basically bar magnet along the axial line as well as along the equatorial line. You might be able to recollect what was the electric field due to an electric dipole along the axial line as well as equatorial line. If the dipole is taken as small one, it was 1 divided by 4 pi epsilon 2 p by r cube as well as p by r cube along the axial line as well as equatorial line respectively. The same thing is coming here as well. If you consider it as along axial line, instead of 1 divided by 4 pi epsilon naught, here you are having what? Mu naught by 4 pi. All right. Instead of 2p by r cube, the only difference is it's going to be 2m by r cube. So 1 divided by 4 pi epsilon naught is replaced by mu naught by 4 pi, p is replaced by capital M. That is the only difference. And while coming to the equatorial line, so here it was axial line. All right, and while coming to the equatorial line, you can have the expression there. It's mu naught divided by 4 pi m by r cube. See, here it was 2m by r cube, and here it is m by r cube. Exactly the same thing. The same formula is coming here for a given angle theta. All right, so there it is again, mu naught divided by 4 pi m by r cube into 1 plus 3 times cos square theta raised to 1 by 2, isn't it? Mu naught divided by 4 pi m upon r cube into 1 plus 3 cos square theta all raised to 1 by 2. Exactly the same formula. I repeat once again, the only difference is that 1 divided by 4 pi epsilon naught is replaced by mu naught by 4 pi, capital P is replacing P there. All right, moving to the next, that is the torque acting on a magnetic dipole. There, in case of electric dipole, we had the mathematical expression as P sine theta. So here it is going to be MB sine theta. All right, so there it was P sine theta, here it is MB sine theta. Then work done in rotating, there it was P cos theta 1 minus cos theta 2. Here it is going to be MB cos theta 1 minus cos theta 2. There the potential energy was minus of P cos theta. Here it is minus of MB cos theta. All right. Now Coulomb's law in magnetism, we explain about the electrostatic force of attraction as well as repulsion between 2 point charges. That was 1 divided by 4 pi epsilon naught q1 q2 divided by r square. And here in case of magnetism, if two magnetic poles of pole strength m1 as well as m2 do interact, though unipole does not exist, but the interaction can be considered, and that study can be made based on that. So in that case, the magnetic force of repulsion or attraction, there it was 1 divided by 4 pi epsilon naught q1 q2 by r square. Here it is going to be mu naught divided by 4 pi m1 m2 divided by r square. That is the only difference. Next is for a current carrying loop. For a current carrying loop, so you all know that current carrying loop behave as a bar magnet, isn't it? So exactly in the same way, a bar magnet was behaving in the same way, current carrying loop also will behave in the same way only. So if a bar magnet was having a magnetic moment, then what will be the magnetic moment associated to a current carrying loop? So if the current carrying loop, if the current flowing through the loop is I, area of cross section is capital A, then the magnetic moment associated with that is going to be simply I into A for single loop. And if you are having capital M number of turns, just along with the same expression, it need to be n times I into A. That is the only difference. All right. Now, if I am having a bar magnet kept inside a magnetic field, and that is in equilibrium condition, that means the direction of magnetic moment is aligned in the same direction of external magnetic field. Okay. Now, if you slightly disturb that, okay, like for example, it's kept in this way, in the equilibrium condition. Now, if I slightly disturb this, so what will happen? It will keep on oscillating like this. Okay, it will be oscillating in this manner. I repeat, magnetic field is in this direction, the same way. So here you can see this is south and here this is north. In this way it is kept. So at equilibrium condition it will be like this. So if you slightly disturb this and leave, so it will be oscillating in this manner. It will be oscillating in this manner. Okay, so this is a vibration and this is a periodic motion. So once it is a periodic motion, definitely there will be a time period. So we are telling about that time period here. Time period T is equal to 2 pi into under root of I divided by M into B. All right, where what is capital I? It's not current. Capital I is moment of inertia of this bar magnet. Moment of inertia of this bar magnet. All right. Okay. So that was the expression for what? The time period of that oscillation as well. All right. Now, next is magnetic dipole moment of a revolving electron in an atom. That means here in this case, I told you, if there is a current passing through a loop, that current carrying loop behave just like a bar magnet. So if it behave like a bar magnet, then definitely we must be able to identify what could be the magnetic moment for that as well. Now, if I am having an electron moving in the circular orbit, all right, so definitely that gives exactly the same impact that of a current carrying conductor in a circular loop. In that case, what could be the magnetic moment? Capital M, that is again basic expression is I into A only, where I is the current and A is area of cross section. Always remember one thing only, in this case it is moment of inertia. Okay, in this case only it is moment of inertia. Moment of inertia means for a particular rod that is ml square by 12. That means the bar magnet in the shape of a rod, the moment of inertia can be taken as ml square by 12 only. So same thing that is applicable in this case. Now here, while calculating the magnetic moment associated to that of that electron moving in a circular orbit, in this case here the small letter I is current only, A is area of cross section. All right, so now this can be replaced as E into nu, where nu is the frequency, that means number of circular rotations in a time. So E into nu all divided by 2 times pi into r, where r is the radius of that orbit. All right, fine, into, so here's this stands for what? I. All right, multiplied by, here you can see the area is written there, pi into r square. All right, the same expression can be converted in the form of E times nu into r all divided by 2. Just resolving this one, what happened over here? 2 pi as well as 2 pi get cancel each other, this one and this one will cancel each other. All right, so pi got cancel each other, this 2 will be there. So in that way you can have this particular expression. I believe that was okay with you. All right, now if you consider the same, if you consider this for any particular orbit, hydrogen like atom in that way, if you want to explain, if you want to explain that way, then capital M is going to be N into EH divided by 4 times pi into m suffix e, where m is mass of electron and n is an integer. That means n basically stands for the number of orbit, 1, 2, 3, like that you will go. It exactly the same that we do consider for the principal quantum number. The same is applicable in this case as well. Moving to the next, there is some important terms used in describing the magnetic properties of magnetic material. Out of that, the first one is magnetic permeability. Basically, it is mu. All right. So the relation for mu is equal to B by H. All right. Now, what is H? It is magnetic intensity. Okay. So capital H is equal to what? B divided by mu. Basically the same thing. And you know that this H is equal to mu into mu, like we used to explain this formula in this way, isn't it? B is equal to mu naught n into I. Fine. So same thing over there. So this actually we can connect in this way. All right. We can connect just in this manner. So here n times I in that formula. This n times I is basically converted as what? Capital H over there. Next is intensity of magnetization. Intensity of magnetization is magnetic moment developed per unit volume. We represent here it as what? Capital I. All right. And finally, magnetic susceptibility. Magnetic susceptibility is capital I upon capital H. Now here I want to tell you something. All right. Mu, that was B upon H. Mu was B upon H. And magnetic susceptibility, that is what? I upon H. So this is something very, very important. All right. And if you want to finally connect this all, we have got this particular relation, that is mu is equal to what? Mu naught into 1 plus magnetic susceptibility. All right. Once again, I explained the terms. First one is magnetic permeability, that was B by H. Next is intensity of magnetization, that is B by mu. All right. Fine. Next is intensity of magnetization. Here this is intensity of magnetizing field. This one is intensity of magnetizing field, and here this is intensity of magnetization. Intensity of magnetizing field is basically H. All right. And H is equal to n times I. N times I basically. All right. Now, intensity of magnetization is magnetic moment per unit volume. Magnetic moment per unit volume. And here comes the magnetic susceptibility. That is nothing. Intensity of magnetization. All right. Upon intensity of magnetizing field. Intensity of magnetization upon intensity of magnetizing field, that is I by H, is equal to magnetic susceptibility. Here I told you how to connect that this relation. Magnetic permeability is B by H and magnetic susceptibility is I by H. And here comes the final expression that connect magnetic permeability as well as magnetic susceptibility. Magnetic permeability mu, that is equal to 1 plus magnetic susceptibility. All right, moving to the next, that is diamagnetic substance, paramagnetic substance, and ferromagnetic substance. So, based on how the magnetic material get magnetized under the influence of an external magnetic field, we classify the material into 3. That is this: diamagnetic, paramagnetic, and ferromagnetic. Out of these 2, the diamagnetic is the only one that get magnetized in the opposite direction of applied magnetic field. Para as well as ferromagnetic substance that get magnetized in the same direction of applied magnetic field. Now, out of this, ferromagnetic material that gets strongly magnetized and paramagnetic material that get weakly or feebly magnetized, you can say. That is the first hand difference about how we differentiate all the 3. First one, diamagnetic, get magnetized in the opposite direction of applied magnetic field. Para and ferro that get magnetized in the same direction of magnetic field. So, if it is in the same direction of magnetic field, how they are different? First, the first thing is, paramagnet that get feebly or weakly, not that strong, okay, feebly get magnetized in the same direction of magnetic field, and ferromagnetic material that get strongly magnetized in the same direction of magnetic field. All right. Now, so how see one more thing, diamagnetic as well as paramagnetic material we can have in liquid form. So if we can have in liquid form, and once we apply, give an arrangement in this way, what happens, here in one of the limb, the level will immediately go down, and in this case what will happen? The level go up. That is just, here it was repulsion. Okay, so that's why the level is going down, and here it was attraction. That is why that level is going up. And ferromagnetic, we can't have it in a liquid form. That is why that is not considered over there. All right. Now another, the main important, formula wise, I want to tell you something about diamagnetic, paramagnetic as well as ferromagnetic. That is about the permeability. Okay, for diamagnetic, the mu value is what? Less than 1. It is less than 1. And for paramagnetic substance, that is mu is greater than 1, and for ferromagnetic, that is very greater than 1. Alright, so here comes another difference, that is in terms of mu. Here it is less than 1, here it is greater than 1, and here it is very greater than 1. Alright, now next is about magnetic susceptibility. Magnetic susceptibility. In case of diamagnetic, alright, it is very small and negative. I repeat, it is very small and negative. Paramagnetic, it is small but positive. It is small and positive. For ferromagnetic, it is large and positive. Diamagnetic, negative and small. Paramagnetic, positive and small. Ferromagnetic, alright, I mean positive, it is positive, it's large, and it is positive as well as large. So how to connect this one is the very first thing that I told. Diamagnetic material get magnetized in the opposite direction. Para and ferro get magnetized in the same direction. Dia was getting feebly magnetized in the opposite direction. Paramagnet was getting feebly magnetized in the same direction. Ferromagnet, that was getting strongly magnetized in the same direction. So the same thing that we are telling here as well. Magnetic susceptibility is negative, opposite. There it was opposite, here it is negative and small value. Okay, feebly get magnetized, here it is a small value. Here also feebly magnetized means small, positive, same direction. Large value, strongly magnetized, okay, same direction, positive. This is how we consider the difference about what? Magnetic susceptibility for dia, para and ferro. Alright, and in case of diamagnetic substance, alright, the resultant magnetic moment is going to be what? 0, because it gets opposite, I mean magnetized in the opposite direction. So the resultant magnetic moment of the substance is going to be 0, and for paramagnetic, alright, it will be having a resultant magnetic moment, and that is permanent value. Alright, and for ferromagnetic, there also it is going to have a permanent magnetic moment. Alright, so that was the most important differences connecting diamagnetic, paramagnetic as well as ferromagnetic substance. And the last one is the temperature dependence. Okay, the magnetic susceptibility, how it depends on the temperature. Alright, for any given paramagnetic substance, how magnetic susceptibility depends on temperature is, magnetic susceptibility is inversely proportional to the absolute temperature. Alright, and for any paramagnetic substance, alright, so for any given paramagnetic substance, what not a given paramagnetic substance, for a ferromagnetic substance, there is a particular temperature. There's a particular temperature at which it changes its behavior from ferromagnetic substance to paramagnetic substance. I repeat, from ferromagnetic substance to paramagnetic substance, that it will switch its temperature, and that particular temperature is known as Curie's temperature. All right, so that is also a point of importance. All right, okay, then the hysteresis is there, but as per the JEE's updated syllabus, this hysteresis loop is not in the syllabus, so we are not going to discuss about that. Next is electromagnetic induction. All right, electromagnetic induction. So here comes the very first point, that is magnetic flux. As you all know that magnetic flux is the magnetic field lines perpendicularly linked with any given surface. How we can have the basic formula for a small area of ds, and if that is kept in a magnetic field of capital B, the small flux link is marked as d phi is equal to b ds cos of theta, where theta is the angle at which the area vector is aligned with respect to the magnetic field. All right, now the SI unit of this magnetic flux is Tesla meter, or that is also represented as what? Weber. All right, in CGS system, that is very important. In CGS system, sometimes it's going to be represented in terms of Maxwell. All right, and 1 Weber is equal to what? 10 to the power 8 Maxwell. Okay, that is very important. And dimensional formula is ml square t raised to minus 2 a raised to minus of 1. All right, next is about the induced EMF. That means basically it is a law of electromagnetic induction, that is Faraday's law. Basically it says that whenever the magnetic flux linked with any particular coil changes, there will be an induced EMF, and that induced EMF E, is equal to it's equal to minus of d by dt of phi. It's basically minus of d by dt of phi. Alright, that negative signs says what? The induced EMF opposes the change in magnetic flux. Alright, and if you want to calculate the induced current, I repeat, if you want to calculate the induced current, basically it is induced EMF by resistance. So you can see a term over there, that is I is equal to induced EMF divided by resistance, that is marked over there. Alright, and we all know that induced current is basically dq by dt. Okay, so dq by dt is now 1 upon r into d phi by dt. I'm just telling about the magnitude. Alright, in that state what happens, you know, dt and dt will cancel each other. You can see that induced charge over here, that is basically d phi by r. So same formula you can have here as well. Okay, I was just connecting that directly. And now if you are having a coil that is rotating at a particular angular speed of omega radian per second, okay, and area of cross section is capital A and the number of turns is capital N, you are having a coil that is aligned, okay, that is aligned in a, that is kept inside a bar magnet, okay, sorry, not bar magnet, that is kept inside a magnetic field, and that is rotating at an angular speed of constant angular speed of omega radian per second. You can, you know, immediately you can connect that with respect to the case of that what you can say, alternating AC generator. All right, in that condition the induced EMF is going to be, so the flux linked is going to be what? Flux linked at any particular point is going to be BAN times cos of theta, BAN times cos of theta, isn't it? Now in this case, if you want to calculate the induced EMF, it's going to be the differential of this, so that is going to be minus of BA, okay, minus of BA n into cos of theta. Theta can be as what? Omega t, isn't it? So into here this is going to be d by dt of what? Cos of omega t. Alright, differential of cos omega t is going to be minus of sin omega t into omega. So the induced EMF you are going to get it as what? BAN times omega into sin of omega t. Okay, so the induced EMF is going to be BAN omega into sin of omega t. And if you want to calculate the induced current, so we need to divide this by resistance. All right, so there you will get this expression for induced current as well. Okay, so that was the expression for induced EMF associated to a coil which is rotating at an angular speed of omega, and there were questions many a times, what could be the maximum value of induced EMF? So here this is going to be the maximum value of induced EMF, and this value divided by the resistance, that is going to be the maximum value of current Imax. Alright, moving to the next, that is Lenz law. Lenz law basically tells about the direction of induced EMF. As you all know that the direction of induced EMF is going to be in such a way that it will always opposes the change in magnetic flux. Alright, next is motional EMF. If you are having a bar magnet, if you have, so not a bar magnet, I don't know why I'm telling all the time bar magnet. If you are having a magnetic field, uniform magnetic field of magnetic field strength capital B, and if you are having a rod of length L that is moving perpendicular to the magnetic field, the induced EMF is going to be BLV. Induced EMF is going to be BLV. And if it is not perpendicular, that means the length is aligned at an angle theta with respect to the magnetic field, then it is going to be BLV sin theta. Basically you must understand something like this. That means, so this is how, if it is there kept perpendicular like this, so here this is the length and magnetic field is in the same way. So in that condition what happens, you know, it's going to be BLV only, magnetic field lines. Are you getting me or what? Fine. Now if the length is aligned at a particular angle, if it is kept in this way, if it is kept, that means you are having L cos theta as well as L sin theta. L cos theta won't be crossing any field lines. Okay, L sin theta will be only crossing the magnetic field line. So in that condition it's going to be BLV sin theta. That is case number 1. There are other cases where this particular rod, you can have a case like this. Yes, it is marked here. It's marked here. So you are having a rod in this way, magnetic field lines are there. So now this is rotated at an angular speed of omega radian per second. In that case, the induced EMF is going to be half half of B omega into L square. Sometimes instead of L they might be using the radius also. Alright, and there are some cases where the area swept also will be given, that capital A. Alright, and instead of omega they will be telling about the frequency. In that case, induced EMF is going to be BA times F. Alright, where area is going to be pi r square. Alright, area is going to be pi r square in that condition. Alright, now next is Fleming's right hand rule. Alright, in order to align my briefing with respect to this one, so Fleming's right hand rule say this is MBI. This is the direction of motion, here this is the direction of magnetic field, and here this is the direction of induced current. I repeat, MBI. Fleming's left hand rule, FBI. Here it is MBI. I repeat, FBI, FBI and MBI. Alright, here this was force experience. This was for force experienced by a current carrying conductor kept inside a magnetic field, and here it is for, here this is for induced current, that is MBI. Alright, okay. Moving to the next, that is eddy current. Eddy's current, nothing, it's another version of induced current, exactly in the same way it was developed in a coil. So here, instead of considering it in a coil, this is going to be for a considerable block, I mean a considerable mass of a fixed volume, or a finite volume, not fixed volume, of a finite volume, something like this. Okay, this is not a coil, this time it's a solid mass distribution, fine, something like this. So in that case also, induced EMF induced is going to be the same thing, that is d phi by dt, and if altogether the path through which the current was flowing that offers a resistance of capital R, then the induced current developed over here, it is going to be d phi by dt, d phi by dt times all divided by resistance R. Alright, again the negative sign, I already told you many times, I am repeating the same. Negative sign stands for the opposite tendency, the opposing tendency of the induced magnetic field against the change in magnetic flux. Next is self-induction. Whenever a current passing through a coil is changed, I repeat, whenever a current passing through a coil is changed, so change in current definitely will change the magnetic flux associated to that link, that coil itself. Okay, so EMF induced in a given coil, I repeat, EMF induced in a given coil due to the change in magnetic flux linked with that coil, just because of the current flowing through that only. I repeat once again, here you are having a coil like this. Let it be a solenoid like structure, not solenoid structure, let it be solenoid. Okay, there is a current flowing through this, and that is I. Definitely magnetic field will be there. If I change the current, so definitely magnetic field linked with this coil got changed. So once the magnetic field linked with this coil got changed, definitely flux got changed. So once flux got changed, what will happen? Induced EMF will be developed. That is known as self-induction. Alright, so that induced EMF E is directly proportional to definitely di by dt. Now to remove this proportionality sign, definitely I will be having a proportionality constant, that is E is equal to L into di by dt. To show the opposing behavior, I will be considering that negative sign. So this capital L is termed as self-inductance, and the general formula for self-inductance is this, that is capital L equals, it's basically mu naught into capital N square times A all divided by L, where capital N is the number of turns. The same thing you can have in terms of number of turns per unit length also. There it's going to be mu naught times, instead of capital N, it's going to be small letter n square. Alright, into A is going to be there in the numerator only, but instead of having small letter L on the denominator, here we are going to have small letter L on the numerator. That is the only difference. Alright, moving to the next, that is energy density of an inductor. Energy density of inductor, you must replace this bus 1 by 2. So the energy stored, not I said it as energy density, not, it's energy stored. Energy stored is half of Li square. That is the energy stored in an inductor. Alright, okay, so here this was self inductance, and there it is energy stored in an inductor. Next is mutual inductance. So if mutual inductance is nothing, like if you are having a coil kept over here, okay, there is another coil kept nearby. So coil number 1 as well as coil number 2. coil number 1 as well as coil number 2. If current is passed to coil number 1, definitely if coil number 2 is within the range of magnetic field of coil number 1, there will be flux linkage, isn't it? Flux, not flux leakage, flux linkage will be there due to coil number 1. So definitely there is a magnetic field produced by coil number 1, and that magnetic field is connected to lobe number 2, I mean coil number 2. So the flux linked with coil number 2 is a non-zero value. Once the current passing through coil number 1 is changed, definitely there will be flux change in coil number 2, and as a result of that there will be an induced EMF, and that induced EMF is equal to, again then the same weight is directly proportional to di by dt. I repeat, I is the current passing through coil number 1, not coil number 2, it is coil number 1. Alright, now to remove this proportionality sign, I can have E is equal to M into di by dt. Again, that opposing nature, to show the opposing nature, I am going to have that negative sign over there. So here you are going to get expression as induced EMF is equal to minus of M into di by dt, and here this proportionality sign capital M, that is known as what? Mutual inductance. It's known as what? Mutual inductance. And here, how to calculate mutual inductance is capital M is equal to, again, mu naught. Okay, there it was n square in the previous case. Here in this case, it was what? N square, isn't it? Capital N square. So here in this case, you are going to have what? N1 into N2. N1 into N2. Again, capital A all divided by L it will be. Alright, and if you want to express this in terms of number of turns per unit length, there is going to be mu naught into, instead of N1, it is going to be small letter N1, N2, A into L will appear on the numerator, you can see. Alright, next is coefficient of coupling. Coefficient of coupling capital K is equal to under root of M all divided by L1 into L2. Alright, it's L by L1 as well as L2 is self-inductance, and capital M is mutual inductance. Alright, next is grouping of coil. Alright, two possibilities we are considering. First one is K equal to 0 and next one is K equal to 1. K is equal to 0 means they are separated by a large distance, so basically it is L equal to L1 plus L2 plus L3 etc. up to Ln if you are having n number of coils, and for parallel combination is 1 by L equal to 1 by L1 plus 1 by L2 etc. up to 1 by Ln. Exactly same as that of the case of resistance. And if it is a case where K is equal to 1, there is a minor change, that is L is equal to L1 plus L2 plus 2 times M if the current is in the same direction, and L is equal to L1 plus L2 minus of 2M if the current is in the opposite direction. Alright, and for parallel combination, the current, if the current is in the same direction, it is L1 L2 minus M square all divided by L1 plus L2 plus 2M plus 2M, and if it is the opposite direction, it is going to be L1 L2, on the numerator it is the same, L1 L2 minus of M square all divided by L1 L2 minus of 2M. Next is alternating current. Alright, so here obviously in the previous segment, I mean the previous chapter, that means while dealing with electromagnetic induction, we came to know how the induced EMF is developed across a coil with capital N number of turns, alright, aligned in a kept inside a uniform magnetic field. So there we came across the expression that induced EMF is E naught sin omega t, and if that is connected across a resistive circuit that offer a resistance of capital R, then we came across the current expression there, isn't it? That was I is equal to I naught sin omega t. The same thing is represented here, and that is represented in the waveform. So for such type of a time varying current, varying current, what could be the mean value as well as what could be the root mean square value of alternating current? Mean value of current for one complete cycle is 0, but mean value of current, if it is mentioned, that means I can fix that is for half cycle. Alright, I repeat, that is for half cycle only, not for a full cycle. For that full cycle it is already 0. So mean value is what? 0.637 times I0, that is also represented as 2 I naught by pi, where I naught is the maximum. Okay, the mean value. In the same way, we can have the mean value for voltage also. The same expression, that is 2 times V naught. 2 times V naught divided by pi is going to be what? The mean value. Alright, and what about the RMS value? RMS value is I naught by root 2, and VRMS is V naught by root 2. Moving to the next, that is reactance. The resistance offered by inductor or a capacitor against alternating current is known as what? Reactants are of two types, that is inductive reactants as well as capacitive reactants. Inductive reactance is represented as XL, that is 2 pi F into L, or that is also like that, the same can be represented as L times omega. All right, next is capacitive reactants. Capacitive reactance is X suffix C, that is 1 divided by C omega, that is 1 divided by C omega. Omega can be represented as what? Omega can be represented as C into 2 pi F, and 1 by F is capital T. All right, so here this is capital T into C into 2 pi. All right, so capacitive reactance. So the graphical variation, so here in this case you can see XL is directly proportional to what? XL is directly proportional to F. So that's why it's a straight line, and here XL is inversely proportional to F. That is why it is a hyperbola there. All right, moving to the next, that is impedance. The resultant reactance, that means the reactance offered by capacitor plus resistance plus inductor, altogether that is known as what? Impedance. The resistance offered by this entire combination, that is known as what? The impedance. So the impedance is mathematically Z, that is under root of what? R square plus XL minus XC, the all square, provided XL is greater than XC, otherwise it is XC minus XC minus XL, the all square. And this we used to calculate from the impedance triangle. So here this is what? XL minus XC, here this is capital R, and here this is Z. So it is the same thing only. Either we can calculate it with the help of impedance triangle, okay, and another format is we can calculate it in this way also. Next is power in an AC circuit, average power in an AC circuit. The general expression for average power in an AC circuit is P average is equal to Vrms into Irms into cos of phi. I repeat, Vrms into Irms into cos of phi. I request you to correct this as cos of phi, okay? Cos of phi only. Fine, that is the general expression that we used to deal with normally. And this cos phi is what? This particular angle. Phi angle is this one. All right, moving to the next, that is current and potential relation in different AC circuits. The first one, it is pure resistive circuit. All right, so if you are having a pure resistive circuit, the current as well as voltage is going to be in the same phase. There is no phase difference at all. All right, so the expression for current, expression for voltage, if it is given as E is equal to E naught sin omega t, then the expression for current is going to be I is equal to I naught sin omega t. All right, now in this case, the average power, everywhere you need to correct it as phi. All right, so in this case, since the phase difference between current and voltage is 0, cos of phi is going to be 1. The average power, that is going to be what? Vrms into Irms. I repeat, it is going to be Vrms into Irms. And if it is a pure inductive circuit, in this case, the current will be lagging with respect to voltage by an angle of phi by 2. That is why that pi by 2, that means here you can see the expression for current as I is equal to I naught sin omega t minus of pi by 2, and definitely voltage is E is equal to E naught sin of omega t. So that phase difference is clearly reflecting over here. So just because of that, while calculating the power value, Vrms into Irms cos phi is here, the phase difference is pi by 2. So cos phi, that is going to be what? 90 degree. Cos phi is 90 degrees, so cos phi is going to be 0. So that is why in that case the average power is going to be what? 0. Average power is going to be 0. So if you consider an inductive impedance triangle in this case, so here this is a pure what you can say, a resistive circuit. So in this case, definitely resistance is not there. All right, so what we can have over here is you can have the voltage here. If I consider voltage as V is equal to E naught sin omega t, I repeat, E is equal to E naught sin of omega t. So here this will be voltage, and the current will be lagging by an angle of what? Pi by 2. Here this is the reference line. All right, so current will be lagging by an angle of 90 degree. All right, and if you consider pure capacitive circuit, in this case, the current will be leading voltage with respect to an angle of what? Pi by 2. So that is why in this case you can see the expression as I is equal to I naught sin of omega t plus pi by 2, and for voltage you are having it as E is equal to sin of omega t. All right, and in this case capacitive reactance, though this is a wrong statement, capacitive reactance X suffix C, that is need to be 1 divided by C omega, and that is need to be 1 divided by 2 pi F into C. So please correct this part. All right, and in this case, since again the phase difference is pi by 2, I repeat, since the phase difference is again pi by 2, the average power, as we discussed in the case earlier case, it is Vrms, Irms cos phi is 0 here, so the average power dissipated in this case is going to be 0. And if you consider again the phasor diagram, all right, in the phasor diagram, that means here this is E naught, this angle is omega t, so the current is leading by an angle of what? 90 degrees. So here this is pi by 2, so the current will be leading by an angle pi by 2. So this is going to be the phasor diagram in that case. All right, next is RC circuit. That means here we are having a resistor as well as capacitor. So equivalent impedance, that is going to be root of what? Root of R square plus XC square. Impedance is going to be root of RC square, R plus XC square. So that you can see here the resistance is the effective impedance is R square plus XC square, and in this case the current is taken as I is equal to I naught sin of omega t plus phi, voltage is equal to E naught sin of omega t. So this phase difference phi, that is the angle between what? That is the phase angle between current as well as voltage term. All right, now in this case, what about the average voltage? Average voltage is going to be, like in this case, you know that the voltage is lagging, isn't it? So since the voltage is lagging, so you may have it something in this way. So here this is VC and here this is what? VR. So definitely this is going to be the effective voltage, that is VR square plus VC square. So you can see that term as well here. All right, and definitely the current will be in this manner. So here this is I, so this is the phase difference phi. All right, okay, moving to the next, that is LC circuit. Fine, so this is not in our syllabus so far because LC oscillation is removed. Moving to the next, that is LCR circuit. All right, so in this case, if I consider here, I am having inductor, capacitor as well as resistance. All right, so in that condition, if I consider the impedance triangle, so here this is going to be XL minus XC, here this is going to be R, and here this is going to be effective impedance. And if I consider the voltage, here this is going to be VL minus VC, here this is going to be R, and here this is going to be the resultant value, again this is going to be phi. So in this condition, if I consider the tan phi value, tan phi means what? Tan phi in this case, I can say tan phi is either XL minus XC. I can say it is going to be either XL minus XC upon R, or in other words, I can say that tan phi, that is going to be what? VL minus of VC all divided by R. So while calculating the power factor, it's again going to be Vrms into Irms into cos phi. All right, fine. So tan phi value is there. And what about cos phi? Cos phi is basically base by hypotenuse, isn't it? That means R divided by Z. All right, so while calculating the power part, we can see that term also here. Moving to the next, that is resonance. In resonance means basically resonance condition is explained for an LCR circuit where the capacitive reactance as well as inductive reactance seems to be the same. I repeat, capacitive reactance as well as inductive reactance is going to be the same. And that condition, what happens once XL is equal to XC, from in this case, that means from the impedance triangle, I can say that this particular entire term, that is going to be 0. That means the impedance offered by the circuit, that is going to be equal to capital R only. So once the impedance is minimum, the current is going to be maximum. That condition is known as resonance condition. And I told you at resonance XL equal to XC. So once I take XL is equal to XC, that's going to happen for a frequency of F is equal to 1 divided by 2 pi under root of L into C. All right, next is wattless current. We just discussed. Once I consider Vrms as well as Irms, and power is, the phase angle, if it is phi, the average power P average, that is equal to what? Vrms into Irms into cos of phi. That means if I resolve this current value, it's going to be Irms cos phi. All right, and here it is going to be Irms sin phi. So out of this Irms, all right, Irms cos phi is contributing to the average power, and Irms sin phi is not contributing to the average power value. So this particular current is known as what? Wattless current. Moving to the next, that is transformer. Okay, in this case of transformer, I mean from the topic transformer, we need to just focus on the transformation ratio only. Transformation ratio is NS upon, like basically it is secondary upon primary. So NS upon NP is equal to ES upon EP, that is equal to IP upon IS. I repeat, K, that is equal to number of turns on secondary upon number of turns on primary, that is equal to voltage across Here it is E, I believe. Yes, voltage across secondary upon voltage across primary, that is equal to current through primary upon current through secondary. This relation is also very, very important. And one more thing, that is about step up transformer and step down transformer. For step down transformer, this transformation ratio is going to be less than 1, and for step up transformer, that is going to be greater than 1. Next is electromagnetic wave. Associated electromagnetic waves, it's a very, very, very small chapter. Equations are very less. First one is displacement current. Displacement current is epsilon naught times d by dt of phi suffix e, where phi suffix e is the rate of phi suffix e is flux between the two capacitor plates, isn't it? Yes. And d phi by dt, we call it as rate of change of electric flux between the what you can say, the capacitor plates again. All right. Now it is Maxwell's equation. 4 equations are there. The first one is closed surface integral of E dot ds, that is equal to Q divided by epsilon naught, that is Gauss theorem. And second one is Gauss theorem in magnetism, that is closed surface integral of V dot ds is equal to 0. And the third one is Faraday's law only, isn't it? Not Faraday's law, that is I'm sorry. It's Gauss law in this was Gauss law in electrostatics, and here this was Gauss law in magnetism. And the third one is Faraday's law. Yes, I said correct. It's Faraday's law. Fine. Faraday's law is what? E dot dl, that's equal to minus of d phi by dt. And the last one is closed integral of b dot dl. This is known as Ampere-Maxwell's law. Closed integral of b dot dl, that is equal to mu naught times conduction current plus displacement current. All right. Moving to the next, that is electromagnetic wave. How to represent the electromagnetic wave? Definitely, this is of basic format. What you know? Y is equal to y naught into sine of omega t minus of kx. The same particular formula it is bearing here. You can have the electric field as well as magnetic field moving in a positive x-axis direction here. This negative sign says that it is moving along positive x-axis direction, and and if it was having positive signs, that means that is traveling along negative x-axis direction. All right. And next one particular part is about the speed of light. So speed of light in the sense speed of electromagnetic waves only. So you can have the expression for that as E is equal to 1 by root of mu naught divided by epsilon naught. And if the magnitude of E naught as well as B naught is given, I repeat, if the magnitude of B naught as well as E naught is given, in that case the speed of propagation, that is marked as what? E by B. In this case, if it is traveling through air or vacuum, it's going to be E naught by B naught is equal to small letter c, that is speed of light. Next is it's the pointing vector, that means in which direction it is propagating. So there you can have the expression as S, that is equal to 1 divided by mu naught times capital E cross B. Fine. This is known as what? Pointing vector. All right. Fine. It is known as what? Pointing vector. This basically tells about the direction in which the energy is being transmitted, or in other words, they say that this is the direction of propagation also. But since once we precisely says that is the direction in which it is being transmitted, so we used to represent as S is equal to 1 divided by mu naught times E cross B. Next one is the energy density. Energy density is basically 1 by 2 times E naught. It's not E naught. Energy density, it is going to be half of epsilon naught into E square, and here it is 1 by 4 times epsilon naught into E naught square. So here this is average value, and here this is the maximum value of current. So please don't forget that. Next is the average magnetic. So average energy density in the magnetic field, and here it was in electric field, and here it is in magnetic field. So the difference is here this is half of epsilon naught into E square. So here this is half of B square divided by mu naught, and here it was 1 by 4 times epsilon naught into E square and E naught square, and here it is 1 by 4 times B naught square divided by mu naught. All right. So just try to understand this. This is RMS value. Again, this is RMS value, and here this is maximum value. So please don't get confused. And the next one is intensity. So while coming to the intensity of the electromagnetic wave, that is basically energy delivered per unit time per unit area, that is half of epsilon naught into E naught square times small letter c, where small letter c is speed of light. Next one is linear momentum. Linear momentum is basically U by C only, where C is again speed of light. Fine. And next is here one more thing. Here this is the case where it is being completely absorbed. All right, completely absorbed. And if it is being reflected, what will happen? Here this is going to be B is equal to 2U by C. That is very, very important. And yes, that is mentioned here as well. So that's going to be 2U by C. All right. Next is electromagnetic spectrum. So you basically that this is a tabular column. All right. And questions are generally asked from this area. There I'm telling you how electromagnetic waves. Obviously, you know about the series from here. This radio wave, microwave, isn't it? radio wave, microwave, RM, fine. Next one is what? Infrared. Next is light, ultraviolet, X-ray and gamma ray. RMI, Lux, G. Alright. Radio wave, microwave, infrared, visible light, ultraviolet, X-ray and gamma ray. Basically, what you must learn out of here is, first one, how these rays are being produced, alright, or how they are generated. Second one is, what are their wavelength range or frequency range. Next one is their uses. This is very important thing. Basically, match the following or either from match the following type or MCQ type the questions are, but this is the category we can classify that into. So you must go through that section as well, and if you can identify any code of your own to keep the things in mind, that is very good. And this particular order, all right, that is in the increasing order of energy, increasing order of frequency and decreasing order of wavelength. That was all from the recap video of module 2. We will be meeting soon with the detailed discussion of another module soon. All right, till then, take care, bye bye and happy learning.